Welcome! In this video, we'll tackle LeetCode problem number 248, Strobogrammatic number 3. This problem challenges us to count strobogrammatic numbers within a given range, low, high. Strobogrammatic numbers are fascinating because they remain the same when rotated 180 degrees. Let's dive into the details. In this problem, we are working with a special type of number called a strobogrammatic number. These are numbers that look the same even when rotated 180 degrees. For example, numbers like 69 foot, 88, and 818 remain unchanged when flipped upside down, while a number like 962 does not. The task here is to find how many such strobogrammatic numbers exist within a given range. The range is defined by two strings, low and high, which represent the lower and upper bounds of the range, respectively. Both low and high are given as strings to accommodate very large numbers, and the result should be the count of all strobogrammatic numbers that fall between these two bounds, including the bounds themselves. This introduces an interesting challenge because the input strings can be up to 50 characters long, making it crucial to account for efficiency in our solution. To clarify how this works, let's look at some examples. In the first example, we are given low equals 50 and high equals 100. The strobogrammatic numbers within this range are 69 foot, 88, and 96, so the output is 3. In the second example, the range is from low equals 0 to high equals 10. Here, the valid strobogrammatic numbers are 0, 1, and 8, which again results in an output of 3. These examples illustrate how the numbers are symmetric under rotation and why only certain numbers qualify. Now consider another example where the range is from low equals 100 to high equals 200. For low equals 100 and high equals 200, the strobogrammatic numbers in this range are 101, 111, 181, and 191, making the output 4. These examples highlight the importance of identifying strobogrammatic numbers efficiently, as the range can include both small and large numbers. Additionally, there are several constraints to keep in mind. Both low and high will always be valid strings representing non-negative integers, and it's guaranteed that low is less than or equal to high. The digits allowed in strobogrammatic numbers are limited to 0, 1, 6, 8, and 9. Any number containing other digits, such as 2, 3, or 7, cannot be strobogrammatic. Special cases like single-digit ranges or ranges with no valid numbers also need to be handled. To summarize, this problem combines the challenges of working with both numeric ranges and the symmetry properties of strobogrammatic numbers. Given the constraints, it's essential to efficiently generate and validate strobogrammatic numbers within the specified range, especially since the input strings can be as long as 50 characters. This means we need to avoid converting these strings into integers, as they may represent values too large to handle with standard numeric types. Instead, our solution must work directly with the string representations of the numbers. Additionally, careful attention is needed to ensure that symmetric rotations, particularly for digit pairs like 6 and 9, are correctly handled to produce accurate results. To tackle the problem of counting strobogrammatic numbers within a given range, we considered three main approaches. The first approach, brute force, involves generating every number between the given bounds and checking if each one is strobogrammatic. This is done by converting the number to a string and verifying whether its digits form valid strobogrammatic pairs, like 6 and 9 or 8 and 8. While straightforward, this approach becomes computationally expensive for large ranges because it processes every single number, even those that aren't strobogrammatic. The second approach, recursive backtracking, focuses on generating only valid strobogrammatic numbers directly. By constructing numbers digit by digit and ensuring symmetry at every step, this method avoids unnecessary computations. Additionally, invalid branches can be pruned early, such as when a partially constructed number exceeds the upper bound. This makes the process far more efficient than brute force. Both methods highlight different trade-offs in terms of complexity and efficiency. Continuing with recursive backtracking, once a potential strobogrammatic number is constructed, it is validated against the provided range, low, high. This approach has a theoretical time complexity of 5 n/2 for n-digit numbers, as there are 5 valid strobogrammatic pairs to consider. However, pruning invalid paths early significantly reduces the actual runtime. While efficient, this method requires careful handling of edge cases, such as numbers with leading zeros or numbers that exactly match the bounds. The third approach we considered was iterative construction. This method also builds strobogrammatic numbers but does so iteratively, starting with a base set of 1-digit and 2-digit numbers. It then layers additional digits to preserve symmetry, stopping when the numbers exceed the length of the upper bound. While conceptually similar to backtracking, iterative construction is less efficient because it generates all possible numbers before filtering those outside the range, leading to higher memory usage and slower performance in practice. The chosen strategy for this problem is recursive backtracking, as it strikes the best balance between efficiency and simplicity. A key realization is that strobogrammatic numbers are symmetric by nature, which means we only need to construct half the number and then mirror it to generate the full number. This drastically reduces the search space. Additionally, there are only a limited number of valid digit pairs such as 0-0, 1-1, 6-9, 8-8, and 9-6, which makes selective generation feasible. By pruning invalid paths early, such as stopping recursion when a partially constructed number exceeds the upper bound, we avoid unnecessary computations. While recursive backtracking requires managing recursion depth carefully, it is more space efficient compared to iterative construction and far faster than brute force. These observations make it the most practical choice for solving the problem within large ranges. Recursive backtracking was chosen over other approaches for several reasons. Brute force, while simple, was too inefficient for handling large ranges due to the need to generate and validate every number. Iterative construction was also ruled out because it requires generating all possible strobogrammatic numbers upfront, leading to higher memory usage and slower performance. In contrast, recursive backtracking efficiently prunes invalid numbers early and uses straightforward recursive logic to construct only valid numbers. In terms of complexity, the time complexity is O(5)(n/2), as we only explore combinations of the 5 valid digit pairs symmetrically. The space complexity is O(n), which accounts for the recursive call stack used to build numbers. This combination of efficiency and simplicity makes recursive backtracking the optimal solution for this problem. To solve the strobogrammatic number 3 problem, the goal is to count all strobogrammatic numbers within a given range, defined by the inputs low and high. A strobogrammatic number is one that appears the same when rotated 180 degrees, such as 69 or 101. First, we need to understand the valid strobogrammatic digits. These include pairs like 0, 0, 1, 1, 6, 9, 8, 8, and 9, 6, as well as single digits like 0, 1, and 8, which are symmetric on their own. Next, we focus on generating these numbers recursively. By starting with an empty string and adding strobogrammatic pairs to both ends, we maintain the required symmetry. However, this process must avoid invalid cases, such as numbers with leading zeros, unless the number itself is 0. Finally, we need to ensure that the generated numbers fall within the given range. This is done by constraining the length of the numbers to lie between the lengths of low and high and by comparing each number lexicographically with the bounds to confirm it is valid. The recursive approach is implemented using a helper function, which we can call find_strobogrammatic. This function takes the inputs low, high, and the target length n. For the base case, if the current string reaches the target length, we check if it falls within the range and count it if valid. For the recursive case, valid strobogrammatic pairs like 0, 0, 1, 1, 6, 9, 8, 8, and 9, 6 are added to both ends of the current string to maintain symmetry, and then the function recurses further. Special handling is required for single-digit numbers, such as 0, 1, and 8, when the target length is 1. To ensure we cover the entire range, we iterate over all possible lengths from the length of low to the length of high. For each length, the recursive helper function generates strobogrammatic numbers of that specific length. To track the results, a counter is used to keep a running total of all valid numbers found. Once all lengths are processed, the counter is returned as the final result. The key to solving this problem efficiently lies in exploiting the symmetry of strobogrammatic numbers. By adding digits in pairs to both ends of the string, we inherently maintain the strobogrammatic property. This recursive generation approach significantly reduces the search space compared to brute forcing all possible numbers. Additionally, instead of converting strings to integers for range validation, we utilize lexicographical comparisons. This avoids unnecessary computational overhead while ensuring accuracy. Another critical insight is handling leading zeros. Numbers that begin with 0 are invalid unless the number itself is 0. This condition must be explicitly checked to prevent generating invalid results. Together, these insights allow us to efficiently and correctly solve the problem. The algorithm relies on specific data structures to manage the generation and validation process. Strings are central to building strobogrammatic numbers since they allow easy appending at both ends and facilitate lexicographical comparisons, such as checking if the current number is less than low. A list is used to store the valid strobogrammatic pairs, like 0, 0, or 6, 9, which are referenced during recursive generation. Finally, a simple counter variable is maintained to track the number of valid strobogrammatic numbers found. These basic yet effective data structures ensure the algorithm remains clean and efficient. Analyzing the algorithm's complexity, the time complexity is driven by the recursive generation of numbers. For a range with width W and maximum number length L, the complexity is approximately 5L/2, since there are only 5 valid strobogrammatic pairs. Space complexity is dictated by the recursion stack, which has a depth of L, where L is the maximum length of numbers being generated. Several edge cases must also be handled. For single-digit ranges, such as 0, 9, the algorithm must correctly account for valid single-digit strobogrammatic numbers. When 0 is a boundary value, the algorithm should ensure 0 is treated as valid but avoid introducing leading zeros in multi-digit numbers. If low is greater than high, the function should immediately return 0. For ranges with significant differences between low and high, the algorithm efficiently constrains generation by focusing only on lengths between the bounds. Let's consider an example where low is 50 and high is 100. First, we generate strobogrammatic numbers of lengths 2 and 3, as these are the lengths within the range. For length 2, the valid strobogrammatic numbers are 69 foot, 88, and 96. After filtering, only 69 foot and 88 fall within the bounds. For length 3, the only generated number is 101. After filtering, 101 is valid as it lies within the bounds. Summing up, we count a total of 3 valid strobogrammatic numbers, 69 foot, 88, and 101. The output for this example is therefore 3, demonstrating how the algorithm handles generation, filtering, and counting effectively. Here, we begin by defining the strobogrammatic in-range function within a class called solution. The goal of this function is to count all strobogrammatic numbers within a given range, defined by the low and high inputs. First, we establish a list of strobogrammatic digit pairs, such as 0, 0, and 6, 9, which are essential for constructing strobogrammatic numbers. We also initialize a count variable to track the number of valid numbers we find. Next, we define a helper function, is_valid, which checks whether a constructed number falls within the specified range. This ensures that only numbers between low and high are considered valid. To construct potential strobogrammatic numbers, we use a depth-first search function, DFS. It takes the current number being built and the target length, n, as parameters. If the length of the current number exceeds n, we stop the recursion. If it matches n, we join the digits into a string, check its validity, and ensure it doesn't start with 0 unless it's a single-digit number. If all conditions are met, we increment the count. In the recursive process, we iterate over each pair in strobogrammatic _pairs, appending one digit to the beginning and the other to the end of the current number. After making a recursive call, we backtrack by removing those digits to try the next pair. This process systematically explores all possible strobogrammatic numbers of a given length. Finally, we loop through all possible lengths of numbers, starting from the length of low to the length of high, and call the DFS function for each length. By doing this, we ensure that we account for all strobogrammatic numbers within the specified range. Once the recursive process completes, we return the total count of valid strobogrammatic numbers stored in the count variable. This concludes the implementation, which efficiently combines recursion and backtracking to solve the problem. Here, we start by importing the necessary utilities and defining the solution class. Inside this class, we declare a variable count to keep track of the total strobogrammatic numbers found. We also define a 2D array, strobogrammatic pairs, which contains all valid strobogrammatic digit pairs, such as 0 with 0, 1 with 1, and so on. The main method, strobogrammatic in range, takes two strings, low and high, representing the range of numbers we need to evaluate. We initialize the count to 0 and use a loop to iterate through all possible lengths of numbers, starting from the length of low and going up to the length of high. For each length, we call a helper function, DFS, which stands for depth first search. This function builds strobogrammatic numbers recursively. If the generated number is valid and doesn't have leading zeros, we increment the count. The method finally returns the count of all valid strobogrammatic numbers in the given range. The DFS method continues by checking if the current number exceeds the target length. If so, it returns immediately. If the length matches the target, we convert the current string builder into a string and validate it using the isValid method. This validation ensures the number is within the specified range and doesn't start with a 0 unless it's a single digit. If valid, we increment the count. Next, we iterate over the strobogrammatic pairs array and recursively build potential numbers by adding each pair to the beginning and end of the current number. After each recursive call, we backtrack by removing the added characters to explore other combinations. The isValid method ensures the generated number lies within the range by comparing its length and lexicographical order with low and high. If it's out of bounds, we return false, otherwise, true. This approach ensures we only count valid strobogrammatic numbers efficiently. We start by initializing some key variables. First, we define strobogrammatic underscore pairs, which are digit pairs that remain valid when rotated 180 degrees. These pairs include 0, 0, 1, 1, 6, 9, 8, 8, and 9, 6. We also set self.count to 0, which will keep track of the total number of valid strobogrammatic numbers we find. Next, we note the lengths of the input strings, low and high, which are 2 and 3, respectively. This means we need to generate strobogrammatic numbers for both lengths 2 and 3. For length 2, we use a depth-first search, or DFS, approach. Starting with an empty list, we iterate over each strobogrammatic pair. For example, adding the pair 0, 0 to the front and back creates the number 2000, but since multi-digit numbers cannot start with 0, we discard it and backtrack. Similarly, we try the pair 1, 1, which forms 11. However, this number falls outside the valid range, so it doesn't count, and we backtrack again. When we try the pair 6, 9, it forms the number 69, which is valid and within the range, so we increment our count to 1 and backtrack to explore other possibilities. After handling the pair 6, 9, we proceed to the next pair 8, 8. Adding this pair to the front and back forms the number 88 foot, which is valid and within the input range. We increment the count to 2 and backtrack. Next, we consider the pair 9, 6, which creates the number 96. This is also valid, so we increment the count to 3 and backtrack again. Once we complete the DFS for length 2, we move on to generating strobogrammatic numbers of length 3. Here, we again start with an empty list and iterate over the strobogrammatic pairs. For the pair 0, 0, we add 0 to the front and back, then recursively add a middle digit to form numbers like 080. However, none of these numbers are valid. When we try the pair 1, 1, we generate numbers such as 181 and 101, and find that only 101 is valid. We increment the count to 4. Similar checks are performed for other pairs, but no additional valid numbers are found for this length. After completing the DFS for all required lengths, we find that the total count of valid strobogrammatic numbers for the given input range low equals 50 and high equals 100 is 4. This value is stored in self.count, and we return it as the final output. To further illustrate the solution, let's consider another example where low equals 1 and high equals 10. Again, we initialize the strobogrammatic underscore pairs and set self.count to 0. For this input, the lengths of low and high are 1 and 2, so we generate strobogrammatic numbers for both lengths. Starting with length 1, we perform a DFS. Using the pair 0, 0, we generate the number 0, which is valid. We increment the count to 1. Next, using the pair 1, 1, we generate the number 1, which is also valid, so we increment the count to 2. Finally, using the pair 8, 8, we generate the number 8, which is valid as well, and we increment the count to 3. Now for the numbers of length 2, we use DFS to generate combinations like 69 foot, 88, and 96. Out of these, only 88 foot falls within the valid range, so we increment the count to 4. This gives us a final count of 4 valid strobogrammatic numbers for the input low equals 1 and high equals 10. Returning this result, we move to the last example, where low equals 0 and high equals 0. Here, only single-digit strobogrammatic numbers are possible. Using the DFS approach, we generate the number 0, which is valid, incrementing the count to 1. Since this is the only number in the range, the result is 1, which we return as the final output. This concludes our walkthrough of the solution, demonstrating how the algorithm efficiently generates and validates strobogrammatic numbers for various input ranges. To analyze the time complexity of the solution for strobogrammatic number 3, we begin by breaking it down into its key components. First, the function iterates over all possible lengths of numbers between the given low and high. If the length of low is m and the length of high is n, the outer loop will execute in m plus 1 times. Next, for each specific length k in this range, the solution uses a recursive depth-first search to construct all potential strobogrammatic numbers of that length. At each level of the recursion, the algorithm explores valid strobogrammatic pairs such as 0, 0, 1, 1, 6, 9, 8, 8, and 9, 6, which means there are 5 possible choices for each pair. This results in an exponential number of recursive calls, approximately 5^(, k/2, for numbers of length k. Finally, each generated number is validated to ensure it falls within the range, low, high. This validation step involves comparing strings of length k, making it an O-K operation. Together, these steps determine how the total number of numbers generated grows as the lengths increase. The total number of strobogrammatic numbers generated can be expressed as the sum of 5^, k/2, for each length k from m to n. In the worst case, where the range between low and high is large, this sum is dominated by the largest term, which is approximately 5^, n/2. As a result, the overall time complexity of the solution is O, 5^, n/2, since the recursive construction of strobogrammatic numbers is the most computationally expensive step. Now let's consider the space complexity. The recursive DFS approach uses a call stack, and the maximum depth of this stack corresponds to the length of the number being generated, which is at most n. This contributes a stack space complexity of O, n. Additionally, the algorithm uses a temporary list to store the digits of the current number being constructed, and its size is also at most n. Together with the constant space required for global variables like strobogrammatic _pairs and count, the total space complexity is O, n. When we combine all these factors, the total space complexity of the solution is O, n, where n is the length of the longest number being generated. Now let's compare this optimized approach to a brute force method. A naive solution would involve generating all possible numbers between low and high and then checking each one to see if it is strobogrammatic. For a range of numbers with d digits, this would involve generating approximately 10^d numbers. Since checking whether a number is strobogrammatic takes O, d in time, the total time complexity for the brute force method becomes O, 10 to the power of d asterisk d, asterisk asterisk. In contrast, the optimized approach directly constructs only valid strobogrammatic numbers, reducing the number of generated numbers to O, 5^, n/2. This is a significant improvement, especially when n is large, as the search space is exponentially smaller than in the brute force method. Let's now discuss the best, average, and worst-case scenarios for this algorithm. In the best case, when low and high define a narrow range, fewer lengths are considered, and fewer numbers are generated. Here, the complexity is approximately O, 5^, m/2, where m is the length of low. In the worst case, when the range spans multiple lengths up to n, the complexity reaches O, 5^, n/2. The average case lies somewhere between these extremes, depending on how many lengths are included in the range. The mathematical reasoning behind the exponential complexity is rooted in how the recursive DFS generates numbers. By exploring only valid combinations of strobogrammatic pairs, the algorithm reduces the search space from 10^k, which would result from generating all possible numbers of length k to 5 k/2. This optimization dramatically reduces the computational cost compared to a brute force approach, particularly for larger values of k. When working with strobogrammatic numbers, there are several common mistakes to avoid. One major issue is ignoring leading zeros. For example, numbers like 008 are not valid strobogrammatic numbers, as leading zeros are not allowed unless the number is simply 0. To fix this, make sure to skip candidates with leading zeros during generation. Another frequent mistake involves incorrect bounds handling. Since strobogrammatic numbers can be very large, relying on integer comparison might fail. Instead, use string comparison to ensure the numbers fall precisely within the range, low, high. Lastly, it's crucial to consider symmetry when generating these numbers. Digits like 6 and 9 must be paired correctly to maintain the strobogrammatic property. Stick to valid digit pairs such as 0 to 0, 1 to 1, 6 to 9, 8 to 8, and 9 to 6 to avoid including invalid numbers in your results. In addition to those, handling single-digit cases properly is another common pitfall. Single-digit numbers like 0, 1, and 8 are valid strobogrammatic numbers and must be included, so it's important to add a base case for these specific values. Another issue arises with inefficient recursive implementations. Recomputing the same subproblems or generating unnecessary candidates can drastically increase time complexity, especially for large ranges. To address this, you can optimize your approach by using memoization or switching to iterative methods, which help eliminate redundant computations and improve performance. Understanding a few key insights can help you tackle this problem more effectively during interviews. First, remember that strobogrammatic numbers are rotationally symmetric, meaning they look the same when rotated 180 degrees. This property allows you to generate candidates more efficiently by focusing only on valid digit pairs. Additionally, instead of generating all possible candidates and filtering them later, optimize your approach by generating numbers directly within the range, low, high. Be mindful of edge cases, such as single-digit ranges, extremely large inputs like 10 to the power of 15, or ranges where no strobogrammatic numbers exist. Finally, when discussing complexity, emphasize that the number of candidates is limited by the number of digits in the upper bound, and the use of valid pairs significantly reduces the search space. There are several related problems that can help reinforce your understanding of strobogrammatic numbers. For example, LeetCode 246 focuses on identifying if a single number is strobogrammatic, while LeetCode 247 involves generating all strobogrammatic numbers of a specific length. LeetCode 400 explores digit manipulation within numerical ranges, and LeetCode 9 examines symmetry in palindromic numbers, which is conceptually similar to strobogrammatic numbers. When it comes to solving these problems, there are alternative approaches you can consider. Recursive backtracking allows you to generate numbers digit by digit using valid pairs, though it can be slow without optimizations. Iterative construction, on the other hand, uses queues to build numbers and is more space efficient, but it can be challenging to implement for larger ranges. Dynamic programming is another option, where you use a table to count strobogrammatic numbers for specific lengths. While this approach is faster for ranges with many digits, it requires more setup and complexity. Another useful technique is leveraging string comparison. Instead of converting numbers to integers, which can lead to overflow issues for very large inputs, you can compare the numbers as strings. This approach helps you remain within bounds and avoids numerical errors. However, it does require careful attention to edge cases to ensure the implementation is accurate and efficient. By combining these strategies and insights, you can handle the strobogrammatic number problem effectively, even in challenging scenarios. Great job! To wrap up, we explored how to count strobogrammatic numbers within a range using a recursive generation approach. This problem is a great example of combining symmetry and constraints in algorithm design. Thanks for watching, and don't forget to like, subscribe, and share. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!